In order to determine if a reaction is viable, you need to make sure that the charge, baryon number, lepton number, and strangeness are all conserved. And so you need to figure out what each of these values are for each of the components of the proposed reaction. For charge, leptons have a charge are negative, -1. Antileptons are positive, usually +1. Neutrinos are neutral. And then the U, C, T quark have a charge of +2/3 E, and the D, S, B quarks have a charge of -1/3 E. For baryon number, each individual quark has a baryon number of 1/3, and leptons have baryon numbers of 0. For lepton number, all leptons have a lepton number of +1, and antileptons have a lepton number of -1, and then everything that's not a lepton has a lepton number of 0. For strangeness, it's dependent on the number of strange quarks. And so if there's one strange quark, it's -1. If there's one anti-strange quark, it's +1. And then if there was 2, it would be -2 or +2. If there was 3, and so on. So first, let's look at example problem number 1. So first, let's look at the charge. On the reactants, so mu minus, that has a charge of -1. Then, what's created? So we have an electron, which has a charge of -1, and then we have gamma, which has a charge of 0. Since there's a -1 on the left-hand side and a -1 on the right-hand side, the charge is conserved. We next need to look at the baryon number. Mu minus has a baryon number of 0, electron has a baryon number of 0, and gamma has a baryon number of 0, because none of these are quarks. So then, since 0 equals 0, left-hand side is 0, right-hand side 0, baryon number is also conserved. Next, let's look at the lepton number. Mu minus is a lepton, so it has a charge of +1. A lepton number of +1. The electron is also a lepton, so it has a lepton number of +1. Gamma is not a lepton, so it has a lepton number of 0. +1 equals +1, and so the lepton number is conserved. And last but not least, the strangeness. Mu has a strangeness of 0, electrons have a strangeness of 0, and gamma has a strangeness of 0, because none of them contain the strange quark, or the anti-strange quark. And so 0 equals 0, so strangeness is also conserved. Since all 4 of these values are conserved, this reaction is viable. Now let's look at number 2. So first we need to figure out what each of these are made up of as far as what quarks are present in each of these. So for the proton, it's an up, up, down. For the neutron, it's a down, down, up. And then the proton again is an up, up, down. And the pi would either be a down, anti-down, or an up, anti-up. And these information is usually given. However, for proton and neutron, you have to memorize that it's up, up, down, and a down, down, up. So now let's see if charge is conserved. Protons have a charge of +1. Neutrons have a charge of 0. Then the proton again has a charge of +1, and pi will have a charge of 0. So that is conserved, since +1 equals +1. Now let's look at the baryon number. The proton and neutron are made up of 3 quarks, and so 1/3 plus 1/3 plus 1/3 equals 1. And so each of them have a baryon number of 1. Then for pi, it's made up of 1 quark and 1 antiquark. Antiquarks have a baryon number of -1/3. 1/3 plus -1/3 equals 0, so it has a baryon number of 0. Therefore, with this proposed reaction, the baryon number is not conserved since 2 does not equal 1. But let's still look at the rest of the quantities. So for lepton number, none of these are leptons, so they're all 0, so lepton number is conserved. For strangeness, none of these have a strange or anti-strange quark, so they all have a strangeness value of 0, so the strangeness is conserved. However, since baryon number was not conserved, this reaction is not viable. Now let's look at number 3. Let's figure out what each of these values are made up of. The proton we know is an up, down, because that you have to memorize. The pi positive is made up of an up, anti-down. And then the pi negative is made up of an anti-up and then a down. So now let's look at the charge. Proton has a charge of positive 1. The pi plus, since is a charge of positive 1, and the pi minus is a charge of negative 1. And you can tell that by the positive or negative sign next to the pi. So charge is not conserved, since positive 1 does not equal 0. But let's still look at the rest of them. Let's look at the baryon number. 1/3 plus 1/3 plus 1/3 equals 1. And so the proton has a baryon number of positive 1. However, for both the pi plus and the pi minus, since it's made up of an quart and an antiquart, 1/3 plus negative 1/3 equals 0, so their baryon numbers are 0. And so the baryon number is not conserved. But let's look at the rest. So lepton number, none of these are leptons, so they all have a lepton number of 0, so lepton number is conserved. And the strangeness, none of these have a strange or anti-strange quart, so their strangeness is all 0, so strangeness is conserved. However, since charge and baryon number are not conserved, this reaction is not viable. Let's look at number 4. So we know that the proton is made up of the up, down, the neutron is the down, up, and then we have the beta plus, which we know is just a positron, and then we have the electron neutrino. First, let's look at charge. Proton has a charge of positive 1. Neutrons are neutral and have a charge of 0. The positron has a charge of positive 1. And then electron neutrinos have a charge of 0. So we know that charge is conserved. Next, baryon number. 1/3 plus 1/3 plus 1/3 equals 1. So baryon number of 1 for both proton and the neutron. And then both the positron and the electron neutrino have baryon numbers of 0. So we know that the baryon number is conserved. For the lepton number, protons and neutrons are not leptons, so they have a lepton number of 0. And then for the positron, it has a lepton number of negative 1 because it's an anti-electron. And then the electron neutrino has a lepton number of positive 1. So then negative 1 plus positive 1, 0. So then since 0 for both the proton and 0 for both the products, we know that lepton number is conserved. Strangeness, none of these have a strange or anti-strange quart, so they all have strangeness numbers of 0, and so strangeness is conserved. Since all 4 of these values are conserved, this reaction is viable. So overall, to solve these problems, just go through each of the components of the proposed reaction, figure out their charge, baryon number, lepton number, and strangeness, and make sure that all 4 of these values are conserved throughout the reaction.